Hello and welcome back to Jason Live. My name is Patrick Shea, and we're here with our STEM Role Model series where we learn about careers in science, technology, engineering, and math. Today's STEM role model is Tony Castilleja Jr. Tony is a mechanical engineer in Boeing's Space Exploration Division. He's worked in mission control for space shuttle launches. He's helped build the Boeing CST-100, which is a space capsule. It's designed to transport astronauts to low Earth orbit safely and affordably. He just recently took on a new role within Boeing and is now part of a team tasked with envisioning the future of space exploration. We're going to hear all about that and more in just a moment. But before we do, just want to remind everybody out there that today's program is live and interactive. Anything can happen. One of the things that we want to happen is for you to ask questions that we can pass along to Tony. We also want you to participate in our polls. So to do so, just use the box just below this video window, and we'll try to get as many of you involved as possible today. I also, before we get started, just want to welcome everybody participating in this afternoon's program from Boys and Girls Clubs and other after-school programs across the country. It's great to have you with us today. And it is great to have Tony with us once again. We just had a program with Tony earlier this afternoon, and he's back. He's been with us all day. Welcome, Tony. Thanks for coming back.
Hey, thanks for having me, and hello to everyone all over the country. I'm glad to be here and to share this journey of space exploration. Absolutely.
We're excited to have you and to learn all about all the cool stuff that you do. But let's start off with the basics. You're a mechanical engineer. Why don't you tell us what a mechanical engineer does, and then what a mechanical engineer that works in the space industry does? What's your job? What do you do on an everyday basis?
Right. So mechanical engineering is one of a variety of fields in what we call STEM, science, technology, engineering, and math. And so when we think about engineers, engineers solve problems using their background of math and science. And so when you talk to engineers, they'll talk about learning calculus, differential equations, algebra, and what they do every day. And so when you look at the physics of motion, the calculus behind that physics of motion, it's really what mechanical engineers are all about, but it's providing solutions, whether it is a bionic leg for our bravest that are coming back from war, or it's using the Da Vinci machine device, which provides us pinpoint accuracy using surgeries, or another application is through automobiles, electric automobiles, gas, hybrid vehicles, and the interfaces that are coming more and more common in our vehicles, and most importantly in my world, aerospace, where we build planes, where we build spacecraft, and where we take the history of going to the moon and going to low Earth orbit and bring it to the 21st century. Mechanical engineers really are the ones that are working with devices in motion. You look at a building, probably a civil engineer involved with that, but once an object moves, like a vehicle, from park to drive, a mechanical engineer takes over. So that truly is what mechanical engineering is. And for space, what we do in building the Boeing CST-100 spacecraft, or building any spacecraft in general, is about the human interfacing with the vehicle, from a switch and what happens with that switch when you actuate it, to the door when you open it, to docking with the International Space Station or other types of low Earth orbit destinations or multiple vehicles, and the process of going end to end between that. In each of these images, you see mechanical engineers working with other engineers, civil engineers, structural engineers, human factors engineers, defining and verifying the design as we move forward in this creation of the Boeing CST-100. There you see a propulsion engineer and structural engineers working together, aerodynamic engineers, and so here you see a validation of testing using aerosciences and aerodynamics data. And so it really is about teamwork. As a mechanical engineer in aerospace, you'll be working with a variety of different people with a variety of different strengths and experiences. It's really fun.
It's amazing how big of a team it takes to make something like this happen. I mean, it's a complex thing to launch something into space and to have it come back, especially in the case of human space flight. We've had questions come in even before the event started, and some of those are video questions. We've got one right here from Austin. Let's see what he has to say.
Sure.
Favorite thing that you built, and if
Audio was a little low on that, but Austin was asking, what's your favorite thing that you have made so far? And if you had the chance, would you go into space with the astronauts?
Yeah. Well, looking back at what I've done in just the last 10 years in this exciting aerospace business, my favorite item has been the Boeing CST-100, this spacecraft that has come from idea to reality. And so in building and rapid prototyping the interior, which is a portion of this engineering design process, where we take an idea like creating a point-to-point safe and affordable solution via a space capsule design that docks with the International Space Station, and then validating the design through rapid prototyping. So we'll take and 3D print an early design of a seat like we did in the past and validate our engineering decisions of how a human will interact with that, taking a drill and going out and rapid prototyping components of the vehicle so that we can better emulate entry and exit of the vehicle before we do these low-cost, affordable ways of design and prototype development, product development, so that when we go and actually build the vehicle, the astronauts know exactly what to go buy. Here you see images of that full-scale trainer that I built. That picture right there is exactly what is the proudest moment of what I've been able to do. And so when I think about the ability to go to space and the ability for everyone to go to space, boy, to be a part of this design process, working with experienced engineers, having worked in Apollo, that worked in the space shuttle program, it's an easy question, and it's an easy answer to that question. Yeah, I'd love to go to space if I know that it's safe.
Sign me up too. If there's an empty seat, I'll go.
Absolutely.
One of the things that I certainly didn't realize when we were prepping for this event, and I was just showing some images here of the prototype that you were just talking about, that it actually is just a prototype, but it is a prototype. It's not, the actual space-ready hardware. This is something that you're using to do testing and to get feedback from the astronauts, like we're seeing here. Can you tell me a little bit more about that process?
Absolutely. When you go from an engineering design to engineering build, what we call the systems engineering process, you really have to go and rapid prototype and define the design, and then go validate and test your design. It's like a really long research paper, but instead of just words, we actually do and go build quickly, and 3D printing. Those seats that you see there are 3D printed of the actual design of the vehicle. So we are able to bring the NASA astronauts into the vehicle to interact with where we have the panels and the switches, both in this simulator and both in flight software. So we actually come up with low-cost solutions in our rapid prototype development process so that when we're on the launch pad with that same astronaut that was a part of our design decisions and design integration, they're comfortable and they know exactly how to operate the vehicle. Here in this image, you see a software capability, what we call the Boeing Engineering Simulator, with a young team of engineers from universities across the country, from Cal Poly Pomona to University of Texas and other great universities, coming together, joining the ranks of the experienced Boeing team and going and flying the Boeing CST-100 virtually. To be able to do that today, it's an autonomous vehicle where the human can take over if necessary, but it's an autonomous vehicle for space. If you think Google's cool, being able to get to space point to point on a computer system, computer driven, boy, that's cool. That's 21st century there.
Pretty amazing. We've got another video question here. This one's from Trevor.
Favorite tool and or technique that you use in your job?
What's your favorite tool and or technique that you use in your job?
Tool or technique? Well, I would say the tool, drill. You can never go wrong without a drill and without a 3D printer, that's for sure. The world of rapid prototype and design opportunities that you guys can have today via your science clubs and robotics clubs, building things, working with your hands. And then in senior design, there you see Exhibit A, me working with a drill, experienced engineers and young engineers together, testing out designs. And then techniques, exactly that. Actually, I just answered the question, right? Going from a sketch on a design CAD model, going out and validating that design through test. Test as you fly and fly as you test, as we call it here.
All right, we're going to jump to some text questions that have been coming in. Here's one from Haley from aerospace class. She wants to know, do you come up with the designs that you build? Where do you fit into the design and building process?
Right. Everyone comes up with designs that we're able to build. It's a team effort. If you think the soccer field is the only place you play with a team, you're absolutely wrong. Actually, my biggest fear when I was growing up in middle school was that I would be a little lonely just doing my math problems, my science problems alone. Actually, it's the opposite when you come to engineering. You're working as a team. And so it's together that we come up with those design solutions, whether it's the ergonomics of a seat or the placement of a switch on the console, or how we interact with the vehicle as we go in and out of the vehicle during an ingress and an egress. We get a team of folks that together come up with design solutions. And we get inspired by the vehicles of the past, from Apollo through Space Shuttle, and we look at the technologies and capabilities that we have today. That's the cool thing about engineering, is that when you come out from school, you join an experienced team, you're taught with the latest and greatest technologies, and together you come up with those design solutions. This is one example of testing that we did. This was validation of our landing and recovery system back in May of last year. And so you see 3 main parachutes, taking that experience of design from Apollo and bringing it to the 21st century. Huge parachutes. This is a view, 15 GoPro cameras on this landing and recovery system mock-up of the vehicle coming down to the desert. Some rolling there. Yes, we do have vomit bags in the vehicle. They have vomit bags in typical aircraft.
Do they use them, or you just wait till you get to the ground and clean it up later?
You can use them if you'd like. That way you're a little bit cleaner on the way down. But you see these 6 landing airbags come out. You see the shadow there on the ground there in the dry lake bed just north of Las Vegas. And you see the 6 landing airbags. These are airbags that are reminiscent of technology that we used for the Spirit and Opportunity rovers when they landed on Mars. Really fantastic validation of that technology to be able to provide for the first time a space. And so you see the horizon there coming up and a nice smooth landing of those 3 main parachutes. Really fantastic footage of a validation of a lot of computer work, a lot of math behind that, a lot of equations of motions validated with that beautiful test. That's the cool part of what we do, getting to go out there and see it in action.
We've got a couple of related questions here from Sarah and Marie. They want to know, what is the malfunction you are most worried about when building a spacecraft, and what's the most difficult thing you've encountered when building a spacecraft?
Right, so when we look at a vehicle, it's what we call the vehicle to be fail-safe, this redundancy in every single system. We know space is an inhospitable environment. It's tough out there, and by tough, there's no air. You know, the International Space Station that revolves around us 24/7 with astronauts up there relies on a finite amount of air that is recycled each and every day. And so safety is paramount. Being able to come up with design solutions that allow us to be in that inhospitable environment. And one of the biggest pressures is obviously when we look at and when we're orbiting around the Earth, what we call micrometeorite debris. That's just one issue. You know, so we operate and we create a design that is robust enough with adequate safety measures that can meet that design, because at the end of the day, the most important person on that vehicle is the NASA astronaut, who's one of the most bravest individuals to go up to space. So we work together to solve that one of our toughest problems, absolutely.
Great. The question continue to flow in here. This one's from Noah. Have you ever had a shuttle you launched return to Earth? Or maybe a better question is, has one of your the shuttles that you were involved in not returned to Earth?
Right. You know, like we said, when we look back at the history of human spaceflight, in the Space Shuttle program, we had Space Shuttle Columbia and Challenger, which taught us a lot about what engineering and the inhospitable nature of space. And so when we look at the achievements of human spaceflight via that space shuttle, what we learned, I actually had that chance through return to flight, STS-107 and onward. I joined Boeing at STS-121, and there you see me during one of those summer internships being at the very top of the shuttle on the launch pad. There's that nose cone of the vehicle, what we call the orbital maneuvering system, reaction control system, OMS RCS, and those are thrusters that once you get into space, maneuver the space shuttle into the right orientations to make the right orbit and dock with the International Space Station.
And
so
Tony,
let me just,
I think it's important to point out here, I mean, as cool as it is that you're standing next to the space shuttle on the launch pad at this point, you mentioned this is an internship. How old are you in this picture?
I was 18 at the time.
18. Yeah. You told us 16 last time.
16 NASA. I joined NASA in 16 during return to flight, and then 2 summers at NASA, and then joined Boeing right after that. And I'll tell you, one of the most fun experiences was seeing STS-131 launch from Cape Canaveral in the pre-dawn sky. To see a rocket launch with your own two eyes, the sounds and the excitement, one of the best experiences I've ever had.
Very cool, and very cool to be involved at such a young age. I mean, it's clearly helped you get to where you are today, and doing the kind of work that you're doing now. And we're going to talk about that career path in just a moment, but we've got a few more questions coming in here related to your current work and current projects. And we're going to grab one right here from Natalie.
Mhm.
And she's asking, what's your favorite spacecraft that has been launched or that you've been involved in?
Well, like any team, the team that we're on right now in space exploration is, the Space Launch System, the Boeing CST-100, and the Space Shuttle. And right now, my favorite is the Boeing CST-100, having been a part of that, using my own two hands to create portions of the vehicle and working with such a fantastic team. I think it's one of the most fun experiences I've had. Absolute favorite, absolute right now, yeah.
Very cool. And we've got some imagery of that as I dig up the next live question.
Right. Here you see the CST-100 docking operations of the International Space Station. This would be a animation of Node 3. And great thing about engineering, we get to make this picture in this video real.
We've got two questions here, somewhat related, probably related, from Camille and Gianni. Camille wants to know what's your favorite part of your job, and Gianni wants to know how hard is it to do your job? And I want to know, is the hard parts your favorite parts?
Right. You learn the most through the hardest challenges, and one of those was the buildup of the CST-100 trainer, where we brought a team of young engineers, straight out of college, interns, and experienced engineers from Shuttle. Just being in the trenches with them and working on this vehicle was one of the most exciting experiences and hardest experiences that I've ever had. Working with my boss at the time, Chris Ferguson, was last commander of the Space Shuttle, and working with a team from across Boeing, bringing in experts from our Boeing commercial airplanes business and bringing the best of Boeing to the design solution. Absolute best favorite part of the job. Now, let's be honest here. Behind all of that is math and science, and so the math is hard. But the great thing about it is that when you work in teams, everyone has a strength, and you'll have the person that's stronger in math, you have the person that's more hands-on, and with all of those folks working together, you'll be able to have a great time in engineering. Absolutely.
All right, I think that's a great segue into our next, the next portion of our program here, where we're going to transition to talk more about your career path. And talk about what it took for you to go from, being the age of some of the members of our audience out there. They're probably in, the 10 to 14-year-old age range. How do you go from being a student in middle school to literally launching things into space, things and people? And we've got a video question here from Kayla. She's going to get us kicked off into this segment.
What kind of courses and degrees do you need to become a mechanical engineer?
What kind of courses and degrees do you need to become a mechanical engineer?
Well, an engineering career, an engineering journey starts today with all of you. It's working hard, getting those high grades. I come from a family that I was the first engineer in my immediate family and first engineer in my entire extended family, first person to get a master's degree. So when we look at the importance of how to become an engineer, is that it starts today, studying hard and getting all the right grades and as high grade as you can. Take those AP courses. Don't let AP mean too hard, because you're going to get college credits, which will help you in the college atmosphere. It starts off with algebra. I took then geometry, algebra 2, pre-calculus, had a fantastic calculus BC teacher here in Houston, Miss Sally Black. Then with partnering with my teacher, who provided me a recommendation, a stellar recommendation, to be able to work at NASA, at a NASA internship, a NASA summer internship at the age of 16. Those two experiences together, plus STEM outreach, allowed me to be able to apply to Rice and to get into Rice, which was my dream school. This is where spaceflight got started. JFK gave his famous "We're going to the moon" speech here. And so, we do things that are hard here. And it goes on with thermodynamics and then multivariable calculus. And each of these courses gives you a well-rounded understanding, so that when you go and design something your senior year at Rice, at UT, at other universities around the country. It's called senior design, where you work with a team of interdisciplinary majors, mechanical engineer, civil engineer, software engineer, which is like the real world, and create rapid prototype designs so that you can present them and create a design solution, whether it's for research in the Texas Medical Center in medicine or for rocket science. It really allows you to work with your hands. So that's the journey. That's the foundation, the launch pad for an engineering career.
There you go. And you just mentioned, many different potential career paths. And this brings us to our next question from Layla. Why did you choose to become a mechanical engineer over any of those other options? What drove you in that direction?
Right. Growing up, my father worked in the construction business. And so that was actually my first introduction to civil engineers. My dad wasn't an engineer himself, but he worked very hard, and he would wake me up at 5 o'clock in the morning on a Saturday morning. I would think I was maybe 13, 12, and we'd go out there, and he'd ask me to go talk to these engineers. That was the first time I defined that via the highways of Houston. And so then growing up, I was between mechanical engineering and chemical engineering, and which one would I do? And because of that NASA summer internship, getting involved with the science club early on, spaceships looked cool. Space shuttles looked cool. And so I decided, hey, well, that's kind of fun. Why don't I choose mechanical engineering? And so I chose mechanical engineering because of the complete portfolio of options you can have, from like we said earlier, from medicine to space to true sciences to applications of all those things. And so aerospace was always the goal for me. And it just shows you that mechanical engineering, there's a lot of opportunity there. Absolutely.
We've got our next question from Clyde Irwin Elementary. They want to know, did you build space shuttles with Legos? Was that part of what drove you to space exploration as a career?
I would like to say that actual question, do they know me? Because I actually did buy a Lego space shuttle just 2 years ago. It was my favorite Christmas present to myself. So yes, absolutely, I would build little cities with Legos. Legos are my absolute favorite thing. And I go to the Lego store every single time, and I see these Lego Technic devices, and I'm thinking that's the coolest thing you can do, just to get your hands dirty and being able to build a real device and do some coding with it. So yeah, I actually do have a commemorative edition space shuttle, external tanks, solid rocket boosters, and orbiter on my desk. Absolutely.
Very cool. Nicholas wants to know, do you feel you learned more from your schooling, more from your education leading up to your career, or are you learning as you go there at Boeing?
It's a mix of both. It's absolutely important to do very well in your coursework, because it allows you to learn how to learn how to problem solve, because these are tough challenges that we're faced with. So getting that bachelor's degree, getting that master's degree is absolutely pivotal to getting into our industry, because it shows us the rigors of the math that's necessary. And so when you work at a place like Boeing, it's an application of everything you've learned. There'll be some classes that you'll apply immediately. There'll be other classes that you apply later. And then there's what we call on-the-job training with those experienced engineers. I have multiple mentors across Boeing that worked in phased arrays antennas, to chief engineers who have worked previous programs in International Space Station, to subject matter experts. I'm telling you, it's a mix of both. And I think I've learned equally, if not more, as I get older from working with the people around me. Absolutely.
All right, we're going to go to Layla again for our next question. She says in your biography, it mentions that your favorite subject in elementary school was art. What kind of impact did that make on you, and does that continue to be a favorite even today?
Yes, because art provides a beauty and emotion to everything that we do. When we design spacecraft, when we design aircraft or satellites, when you think about the launch of a vehicle, it really is a feeling inside, a passion to what we do. And art was actually one of the most important things early in my career. My mother loved music, and so I actually learned how to play viola and performed in Carnegie Hall at the age of 16. 16 was apparently a very pivotal year.
You had a lot going on that year.
Yeah, but the arts have always been very important. And actually now, after I graduated from Rice, I'm diving back into the arts. because it provides color to what we do. We work with drills, we use our math equations, but nothing beats that swelling of a symphony when you see a space shuttle launch. Absolutely.
We've got just one more question in this
Yeah.
segment, and this one comes from Riley, who has clearly read your background and has learned a bit about your family. Let's see what Riley has to say.
Did you try as hard as your brother and sister in college? If not, why?
Did you try as hard as your brother and sister in college?
You know, I'm going to get an email on that one from my sister and my brother. You know, when I look at my family, my father is my definition of hard work. My mother she used to say, la llave del éxito es la educación. The key to success is education. My sister blazed a trail. She was the first in our entire family to go to college. She now works in the oil and gas industry. And my little brother, will always be slightly shorter than me in my eyes, even though he's a little bit taller. He's running on the bridges that my family built. He runs track and doing very well at it. Each one of us, and that's the beauty of science and engineering and going to college, is finding your strengths. And so with that passion, that drive, each one of us cheers each other on, whether it's on the track field, in the oil business, or in building spaceships. It makes for really fun family dinners.
I bet, and it's great to have that very cool support system, both from your parents and your brother and sister. So it's important. It's important to get through hard stuff. When you have good family, it makes it all that much easier. We're going to shift gears now. We've answered a lot of questions. Tony has answered a lot of your questions. I've just been sitting back here doing my thing. But it is now Tony's turn to ask you some questions. We're going to switch over to our polls now. And let's see if we can push that first one out your way. So Tony's come up with these. Let's see how well you do. Here's the first one. He wants to know, how high is space? Is it A, 24 miles? Is it B, 62 miles? Or is it C, 200 miles? And Tony, while we're waiting for folks to submit their answers to this, why don't you tell us your definition of where space begins, without giving away the answer here?
Right, so we call it the von Karman line. And so that separates the atmosphere to this, what we call just above lower. That line defines where space is, and that's where we send high-altitude balloons to satellites, and the International Space Station is just above, a couple hundred kilometers above that line, and so it's a cool place. It's getting more and more traveled these days.
Cool place, the edge of space. So we have folks are out there, they're voting. I can see their responses coming in, and I can tell you right now, 62 miles and 200 miles are tied. Actually, 200 miles just took a slight lead. That has about 50% of the vote at the moment. We're still getting some responses in, but why don't you tell us what is the correct answer here, Tony?
Sure, the correct answer is B, 62 miles, 100 kilometers an hour, 100 kilometers. And so if you were listening to, and you were viewing what the Boeing CST-100 is all about, 100 gives the answer away. It's 100 kilometers up in space to low Earth orbit, the definition of low Earth orbit, going beyond that von Karman line and on to the International Space Station. So yep, that's 62 miles, 100 kilometers.
There you go. And we're going to move to our next poll question here. There it is. On a somewhat related note, how fast do you have to go to get into low Earth orbit? Is it A, 1,000 miles an hour? Is it B, 8,000 miles an hour? Or is it C, 18,000 miles an hour? Any of these answers, Tony, these are pretty serious speeds. How do you get up to that speed, whatever the answer is? And then we're going to keep an eye out for the kids' answers coming in right now. But any of these, you got to get moving pretty good.
Yeah, you're going to get a couple of speeding tickets on Earth, that's for sure. You know, going to space is what we call the tyranny of the rocket equation, because we can get to space, a typical human being, that mass, theoretically can get to space pretty high. Now, the issue is, in order to get higher, you need to add more mass. And even to take more people, you need to add more mass. Well, now you have the mass of the person and the rocket behind it, so now you have to add more mass and more fuel. to be able to go up into space. And so when you look at the Saturn V rocket, when you look at the space shuttle, you see these plumes coming off of the vehicle. And that means that they're going, without giving the answer away, above the speed of sound. And they're breaking those barriers. And so it'll be interesting to see what people think that speed is.
Well, I'll tell you what they think right now. At the moment, all three answers have some votes, but we are currently tied. B and C are tied. Each have 40%. So
Yeah.
what is the correct answer here, Tony?
The answer is C, 18,000 miles an hour. Now think about that. You look at the Saturn V rocket, which is the largest rocket that has ever been built by mankind in the history books. You look at the space shuttle, and then you look at our new vehicle, the Boeing CST-100 for low Earth orbit and the Space Launch System for deep space exploration. And so those large masses have to go from 0 to 18,000 miles an hour. And many people just point up to go to space. Well, in actuality, you go up, and then you start curving. You start curving to get into that orbit plane. So there you see an example of the Space Launch System. The Boeing CST-100 is for low Earth orbit, and with the Space Launch System, we are now going to be able to propel the Orion spacecraft for deep space exploration. And so that gives us a multitude of opportunities and makes this business really exciting to be a part of.
We're going to talk more about deep space exploration and all kinds of futuristic options in just a couple minutes, but we're going to take our last poll question here. How long does a typical spacecraft take to get into space? Is it A, 8.5 seconds, B, 8.5 minutes, or C, 8.5 hours? So again, Tony, we're talking going from the surface of Earth into, in this case, we're talking low Earth orbit. Is that fair to say?
Pretty much low Earth orbit, yeah. And if you
Okay.
think about it, two of these will go by during this, well, one I think went by while you were speaking, and the second one went by since the beginning of this this webcast.
It feels like 8.5 hours sometimes. But, so we've got responses coming in. 50% so far. Actually, it's changing. 40% think 8.5 seconds, 20% 8.5 minutes, and 40% 8.5 hours. So we've got a real mix of answers here. But they either think it's the shortest or the longest of these options. Why don't you tell us what the right answer is?
You know, and with every engineering question, the other question is, what are your assumptions? And so the correct answer is 8.5 minutes. The reason being is I define typical spacecraft as a space shuttle. The space shuttle, when it launched, went from 0 to pretty much low Earth orbit, and we would get to what we call main engine cutoff, and that happened about 6.5 minutes into the flight profile of the vehicle. And then you use those OHMs RCS thrusters, that picture that I was standing next to orient yourself before the International Space Station existed, just to get to an orbit, to either drop off the Hubble Space Telescope or another type of satellite. And then when the International Space Station was built and completed because of the space shuttle, it would get to the right orbit for about 8.5 minutes and then rotate around and play catch-up. It's literally a cat and mouse game over the heavens.
There's a lot to think about. We are going to move on now. We're going to get back into our Q&A mode and just kind of go rapid fire with the time that we have left here.
Sure.
This next one's from Andrian. He's asking, what did you do to practice building? So you've talked a lot about, getting the drill out and doing these rapid prototypes. How did you get good at that particular set of skills?
Well, as a kid, Legos, and being able to work with those. Now, as a professional, I will admit I was working with my friends. My friends have a lot of different skills and being able to work with their hands, and each one of them has a lot of strengths. So it's learning by doing. But I'll tell you, an engineer being able to do both is quite a powerhouse. And so really good stuff there. I learned that as I went. So now I'm really good at using a drill. I have a master's degree in using a drill.
There you go. Zach's got the next question. Who is the most famous person that you've met besides Neil deGrasse Tyson? And have you met him? Was that something that he got out of your profile responses?
Yeah, I actually was able to meet Neil deGrasse Tyson. He gave a speech here at Rice University. You know, how the irony of being able to meet him because of the university I went to. He was the keynote speaker for graduation, and so after the graduation speech, I was very fortunate to be invited to a luncheon with him there, and he was talking about the great work right now doing Cosmos. And so really, really fantastic person. And the other really cool famous people is, we all saw the Red Bull Stratos jump. I didn't get to meet Felix, but I got to meet the team behind Felix Baumgartner's jump. And so those folks are go-getters and define, breaking the speed of sound, literally. Getting to meet them right here in Houston was a really great blast.
And you were just telling me about somebody else you met just earlier this week. Is that something you can talk about?
Yeah, when we look at the history of Boeing and we look at the beauty of human spaceflight, none other person comes to mind than Bill Nye the Science Guy. Got to be a part of a project with him. So really great people. And when we think about engineering and the cool factor of engineering, boy, those are our heroes.
All right, we're getting our next question here from an anonymous guest wants to know, what's the hardest thing you've ever done?
Hardest thing I've ever done. I will tell you, to become an engineer, it's tough. And there was one course I took actually right here at Rice that I didn't do too well in a course on control theory. And it was a tough break for me because I had pushed so hard in my other engineering classes. You did everything you had to do, right? Study, stay up late, work on all the example problems. And here I sat in class, took the test, and I just did badly. The great thing about Rice is the professor. So I talked to the professor that was teaching the course at the time. She said, "Don't worry about it. This happens to students. It's not a detractor in any sense of the word. I'm going to have the course next semester. Come take it again." Talked with my professor and mentor, best friend, Dr. Houchins. He gave me another piece of advice. Don't worry about it. You're going to do fine. And I still wasn't convinced. I went to the chair of the mechanical engineering department, Dr. Barrera, who comes from a similar background that I come from. And so that was very key. Those three perspectives really helped me get past that hurdle because, like I said, every engineer is strong in different areas. And so that was an area I had to study some more. But that's where good study groups come through.
Great. We've actually got three somewhat related questions to ask you at the same time here. What's your favorite thing that you've built? What's the best invention you ever came up with? And what's your favorite invention?
Well, right now, up until now, it's that interior of the Boeing CST-100, getting to work with a really cool team from across Boeing, from the folks who do lighting in airplanes. There you see the Boeing blue sky interior, kind of awash there in the background. This picture literally defines the coolness factor of the most favorite thing I've done. My favorite, the best invention. Well, actually, I was actually a part of a team during my senior design course that a very experienced NASA engineer had been looking at rotorcraft landing of a space capsule. So as a space capsule lands, deploying helicopter type of hardware and be able to land under basically autonomous flight using scramjets. And so, these are new technologies, and that's really what engineers can come up with, is look at ways that we currently do things and make them better. We look at the rotary phone, which probably everyone on this webcast doesn't know what that is. But look at, let's say, the iPod Nano to today, the iPhone, the amount of innovation that happened in between.
It's pretty amazing. Anna and Sarah have a question for you. They say, we heard that you work on lassoing asteroids. How do you do that? And why don't you use this opportunity to tell us about this new role that I described earlier at the beginning of the program, where you're thinking about the future of space flight and space exploration and how to make all of these things commercially viable. Get us into that area.
Yeah, well, here in Texas, we know how to lasso things, it seems. But more importantly than that, NASA is very strong. NASA has a fantastic vision to be able to go and lasso an asteroid, learn more about it, more about things that orbit around us, going to the moon and Mars. And so what we're doing today is working with NASA to be able to achieve that vision and mission, looking at the technologies that we need today to invest in today in adjacent markets and other types of markets that we're going to be able to go and study an asteroid. NASA has done missions towards the moon where we impact the moon to see the data we get out of it. Same thing with an asteroid. The future is really, really starting to get just beyond words in terms of going and looking at the moon and looking beyond, looking and seeing the answers of our universe, looking towards the past while looking into the future. So when we talk about lassoing asteroids, I wish I had a rope, but being able to identify those technologies that we need today so that we can go do those deep space missions with the Space Launch System.
And when we talk about these projects in the future, you will certainly be involved in those, given that you're pretty early on in your STEM career. But by the time we're talking 10, 15 years out, kids that are watching out there today are also going to be involved, and they will be involved because of their education and things that they're learning today and through college. And we've got a couple questions here, one from Mary and one from Bobby. They're about STEM education. So Mary asks, what do you think is the most important points middle school students should know and understand about STEM? And Bobby wants to know, if you could change one thing about the current STEM education system, what would it be? What do we need to prepare this next generation of engineers and explorers?
If you were to ask me 10 years ago that I would be able to be a part of this exciting business, I would have kind of questioned. My dream was to work on the space shuttle, and I always looked at the Boeing CST-100 as a dream continued. And now, looking at new technologies and adjacencies, it's that much more. And so when I look back at middle school, it's really looking at experiences and being able to find cool ways of bringing that textbook to life, whether it's an algebra equation and doing visual programming. There's different types of robot programs out there. When we look at experiences that you can have to mentors, actually one of the biggest things that I think could really change the way we look at science and STEM education here in the United States is mentorship. Through my professor, Dr. Houchins, we've founded the DREAM STEM Outreach Program here in Houston, where we provide Rice students to high school students. I think every high school student, every middle school student will succeed and can and will succeed and will get to become an engineer because of mentors. People that look like you, act like you, like the same music, but at the same time studying engineering and doing these rapid prototype kind of clubs where you're working on rockets, where you're working on FIRST robotics, where you're working on different types of projects working together. Because at the end of the day, it's about helping each other.
Well, you have helped us out tremendously, and you are our role model and mentor. And we're going to wrap up our event today with this last question, which I think really sums it up for everybody. This is a question from Miss DeMaio's class. They want to know, what makes you an unstoppable hero? And what I love about this question is that they're not questioning whether or not you're a hero. That is a given. They just want to know what makes you unstoppable and a hero.
Newton's law, action, reaction. No, I'm just kidding. But when I look at everything that I get to do, it's the people that I get to work with. And when I look at, I'm very appreciative for that question, because I look toward my heroes. There's great organizations like Great Minds in STEM, the Society of Hispanic Professional Engineers, that have provided role models that are my heroes. Here at Rice, we have Dr. Richard Tapia, who received the top National Medal of Science from President Obama. He's a mentor of mine right here at this university. I'm a reflection of mentors that have given of their time. And so when I do these kinds of talks, I talk about the excitement of our business, because people have done that for me. And as long as people do that, I'm going to be right here sharing these great journeys with everyone that I meet.
Well, I think we could sit here and talk to you for another hour if we could, but unfortunately, we have to wrap up. We really appreciate you taking the time and sharing all of this insight into the kinds of work that you do and what got you to this point, and inspiring this next generation of mechanical engineers.
It's a fun business. I can't wait to see you guys in 8 to 10 years helping us build the future. It's going to be a great time in this business.
I agree. Thanks for joining us, Tony. We are going to look now to next week when we come back down to Earth and even peek inside the Earth with our next STEM role model. Her name is Patricia McQueen. Patricia is a volcanologist and a geophysicist. She studied active volcanoes in Central America, making precise gravity measurements to better understand their internal structure. Doing so can improve our ability to monitor volcanoes and potentially forecast future eruptions. You can learn all about that and ask Patricia questions about her STEM career path next Thursday, March 27th at 1:30 p.m. Eastern. That is all the time we have for today. Once again, for Jason Learning, my name is Patrick Shea. We'll see you next time on Jason Live.